Unlimited clean energy. Sounds like a dream.
It does.
That's the promise of fusion energy, and it's been generating a lot of buzz.
It has. It really has.
People are saying it might not be science fiction, but possible in our lifetime. Today we'll explore what fusion is, the hurdles, and if it could transform our world.
It's a fascinating topic, especially now with all the recent developments.
All right, it feels like we're on the cusp of something big.
Yeah.
Let's start with the basics. What exactly is fusion?
Fusion happens when you take light atomic nuclei, like these types of hydrogen called deuterium and tritium,
Okay.
and you squeeze them together under immense pressure and heat.
You're talking like sun-level heat and pressure, right?
Way hotter than the sun, actually.
Wow. Okay, so you're squeezing these tiny atoms together, and what happened?
Well, if the conditions are extreme enough, they overcome their natural repulsion and fuse together.
They fuse, so they basically become one, right?
Exactly. They form a heavier nucleus, in this case helium, and that process, that fusion, releases an incredible amount of energy.
So it's like atomic alchemy.
Kind of, yeah. You're taking lighter elements and forging them into heavier ones, releasing tons of energy along the way.
So that's fusion, but how's it different from fission? You know what we use in nuclear power plants today?
Great question, and it's a really important distinction. Fission is all about splitting heavy atoms like uranium,
Right, splitting them apart.
while fusion combines those lighter atoms,
One is breaking down and the other is building up.
and the energy released in fusion is just massively greater than fission.
So fusion is like a superpowered energy source. And the best part, no greenhouse gases, no harmful emissions.
Precisely. Clean, safe, and abundant.
It sounds almost too good to be true.
Well, there's a reason we aren't all driving fusion cars yet.
Right, there must be some catches. What are the challenges?
Oh, there are quite a few hurdles. One of the biggest, as we touched on earlier, is recreating the sun's core here on Earth.
You mean those crazy high temperatures?
Yeah, we're talking temperatures over 100 million degrees Celsius. That's 6 times hotter than the sun's core.
100 million degrees, that's just mind-blowing. What kind of container can even handle that kind of heat?
It's less about the container itself and more about controlling what's inside. We're dealing with superheated plasma.
Plasma.
Yeah, it's this wild fourth state of matter, like a super energized gas where electrons are stripped from atoms.
So it's not your everyday kind of gas.
Definitely not. And containing that incredibly hot, energetic plasma is a monumental challenge.
Sounds like trying to bottle lightning.
A pretty accurate analogy. So yeah, mimicking those extreme conditions is our first big hurdle.
Okay, so challenge number one, extreme heat and controlling this crazy plasma. But how are scientists actually trying to achieve fusion? What are the main approaches they're exploring?
Well, there are 2 main paths researchers are taking: magnetic confinement fusion and inertial confinement fusion.
Magnetic confinement fusion. That sounds straight out of Star Trek.
It does have a sci-fi ring to it, right? Imagine this, a donut-shaped chamber called a tokamak.
A tokamak. Got it.
And inside, you have these powerful magnets creating an intense magnetic field.
Okay.
And that field acts as an invisible force field, trapping the superheated plasma inside, keeping it away from the walls of the chamber.
So we're basically holding a mini sun with magnets.
Pretty much. The plasma gets heated and compressed within this magnetic field, creating those extreme conditions needed for fusion to occur.
That's amazing. Are there any real-world examples of this magnetic confinement in action?
Oh, absolutely. The Experimental Advanced Superconducting Tokamak, or EAST in China, is a great example.
East.
They actually set a world record recently, holding a stable plasma for over 1,000 seconds.
Wait, over 1,000 seconds? That's like 17 minutes?
It is. That's the current record for sustained plasma, and it's a huge achievement.
Wow. So they're making some serious progress over there.
And then you have ITER.
ITER.
It stands for International Thermonuclear Experimental Reactor, and it's even bigger and more ambitious than EAST.
So it's like the ultimate fusion experiment.
It's a global collaboration, with countries all over the world working together to build the largest tokamak ever.
Wow, it's like a global race to build the best star simulator.
In a way, it is, and it shows just how much potential fusion energy holds.
Okay, so we've got magnetic confinement. What about that other approach you mentioned, inertial confinement? How does that one work?
Inertial confinement is completely different. Instead of magnets, this method uses high-powered lasers. Yeah, they focus these lasers on a tiny target containing the fusion fuel.
So instead of a magnetic field, we're using lasers to create the necessary conditions for fusion.
Right. Imagine using a magnifying glass to focus sunlight onto a tiny point, except we're using incredibly powerful lasers instead of sunlight.
That makes sense. And what's the goal here?
The goal is to compress and heat that tiny fuel pellet so intensely that it implodes on itself.
Implodes.
Yeah, the outer layer of the pellet vaporizes instantly from the laser energy, and that creates this inward force compressing the remaining fuel.
So it's like a mini controlled explosion.
Exactly, and the inertia of the imploding fuel, the tendency to keep moving inward,
Okay.
that holds it together just long enough for the nuclei at the core to fuse and release energy.
It sounds incredibly precise, like a perfectly timed explosion on a microscopic scale.
It is, and that's one of the big challenges with inertial confinement.
What do you mean?
Achieving perfect symmetry with those laser beams. They need to hit the fuel pellet from all sides with absolute precision.
So any tiny imperfection could throw the whole thing off.
Exactly. It's like trying to hit a moving target, but on a microscopic level.
I can see why that would be a challenge.
Yeah.
It sounds like you need some seriously advanced technology to pull that off.
Oh, absolutely. The laser systems and target fabrication techniques used in inertial confinement are cutting edge.
It's mind-boggling to think about the level of precision involved.
It is, but it's also incredibly exciting. And then we have those alternative approaches we talked about earlier, like TAE Technologies and Helion Energy.
Yeah.
What sets them apart is that these aren't, those massive international projects like ITER that we hear about all the time.
Right.
These are private companies
Yeah.
with some serious backing and even bolder claims. Let's start with TAE Technologies.
Okay.
They're using a magnetic confinement approach called a field reverse configuration,
Okay.
or FRC.
FRC. Right.
Now, this isn't totally new.
Right.
FRCs were researched back in the 60s and 70s.
So they're reviving an old idea, but with a modern twist.
Exact.
What makes their approach unique?
What's interesting about an FRC is that it's self-organizing.
All right.
The plasma's own motion creates the magnetic field that confines it.
Wow.
So instead of external magnets shaping the plasma,
Right.
it's more like a swirling tornado
Okay.
held together by its own energy.
That's super interesting.
TAE believes that this self-organization could be the key to a more stable and efficient fusion reaction.
So they're harnessing the plasma's inherent properties
Yes,
to their advantage.
to their advantage.
That's fascinating.
Yeah.
What about the fuel they're using?
This is another area where TE stands out.
Okay.
They've chosen hydrogen boron, also known as P11B.
P11, baby.
Got it. What's special about this fuel is that it's considered aneutronic,
Aneutronic.
meaning it produces far fewer neutrons
Yeah.
compared to the more common deuterium-tritium reaction.
Why are fewer neutrons better?
Fewer neutrons mean less radiation and radioactive waste,
Right.
leading to a much cleaner and safer form of energy.
Gotcha.
Think about the long-term implications.
Yeah.
No need for complex tritium breeding,
Right.
simpler reactor designs,
Okay.
and less worry about material damage.
Wow.
That's the holy grail that TAE is chasing.
That's incredibly ambitious.
It is.
But I'm guessing it comes with its own set of challenges.
You're spot on.
Yeah.
Aneutronic reactions typically require much higher temperatures to achieve fusion,
Right.
which puts a lot of stress on the confinement system.
Right.
Imagine trying to contain a plasma that's orders of magnitude hotter than the core of the sun.
Yeah.
That's where TAE's choice of plasma heating comes into play. Neutral beam injection.
All right, break that down for me.
Sure.
How do they heat the plasma to those extreme temperatures?
Essentially, they fire a beam of high-energy neutral particles into the plasma.
Okay.
These particles collide with the plasma particles,
All right.
transferring their energy and heating it up.
Got it.
It's a bit like using a high-powered laser to precisely target and heat a specific point.
Yeah, that's
Gotcha.
interesting.
Yeah.
So TE's approach is all about combining a self-organizing plasma structure
Right.
with a clean fuel source
Yes.
and a precise heating method.
Uh-huh.
Their sights are set on long-term sustainability. Now let's switch gears and talk about Helion Energy,
Okay.
the other contender in this fusion race.
Right.
What makes their strategy different?
Helion has opted for a pulsed fusion approach,
Okay.
aiming to create short, powerful bursts of fusion energy
Right.
that they can directly convert into electricity.
So it's like creating miniature controlled explosions
Exactly.
of fusion energy rather than a constant burn like TE. Pulsed fusion, that sounds like a whole different ballgame.
It is.
How do they manage to create these bursts of energy?
They use a clever hybrid approach
Okay.
that combines magnetic and inertial confinement.
Right.
Picture this. They create two plasma jets and use magnetic fields to guide and collide them at incredibly high speeds.
Okay.
This collision acts like a magnetic hammer, further compressing and heating the plasma to the point of fusion. And it gets even more interesting when you consider their fuel choice.
Okay.
Instead of hydrogen boron, Helion uses deuterium helium-3.
Hold on, anetronic again.
Absolutely.
Didn't we just establish that was a big deal?
It is.
Okay.
But remember, even though both companies are aiming for anetronic fusion,
Right.
they're using different fuels to get there,
Yeah.
and each fuel has its own quirks.
Okay.
While deuterium helium-3 offers the same advantages in terms of reduced neutron production. It has one major drawback.
What's that?
Helium-3 is incredibly scarce on Earth.
Ah, there's always a catch.
Right.
So while Helion might have a faster path to commercialization with their pulsed approach,
Potentially,
they could face a fuel supply problem in the long run.
that is a key consideration. Helion's bet is that they can make their technology work efficiently enough
Right.
that accessing lunar helium-3 becomes economically viable in the future.
Wow.
It's a gamble, but one they seem willing to take.
It's a high-stakes game for sure.
It is.
We've talked about the science, the challenges, the approaches, but ultimately the question on everyone's mind is, when can we plug our homes into a fusion power plant?
Well, we're not quite there yet,
I figured as much.
but we're definitely getting closer. Recent breakthroughs, especially the achievement of net energy gain at NIF,
Right, that was huge.
it sparked a surge in private investment. People are starting to realize that fusion is no longer just a distant dream, but a potential economic powerhouse.
So it's not just governments and research institutions pushing for fusion anymore.
Nope. Private companies are jumping into the game, bringing with them their resources and agility.
Which could really speed things up.
Exactly. Companies like Commonwealth Fusion Systems, they're attracting massive investments and are already planning to build the world's first grid-scale commercial fusion power plants.
Hold on, grid-scale fusion power plants. That sounds incredibly ambitious. What's the timeline on that?
They're aiming to have their demonstration power plant, called Spark, up and running by 2027.
2027, that's just a few years away.
It is. If successful, Spark would be a major step towards proving the viability of commercial fusion power.
So this is really happening.
It seems so.
But before we wrap things up, I'd love to get your perspective on the bigger picture. How do you see fusion energy fitting into our overall energy future?
Well, I think fusion has the potential to be a real game changer, a core part of a diverse and sustainable energy mix.
So you see it working alongside other clean energy sources like solar and wind.
Exactly. It's not about choosing one over the other. It's about having a variety of tools in our energy toolkit.
Makes sense. A balanced approach is key.
Right, because each energy source has its own strengths and weaknesses. Fusion, for example, is what we call dispatchable.
Dispatchable.
It means we can turn it on and off as needed, unlike solar or wind power, which depend on the weather.
Right. The sun isn't always shining and the wind isn't always blowing.
Exactly. Fusion could provide that steady, reliable baseload power regardless of the weather.
That's a huge advantage. Plus, fusion has a much higher energy density than most renewables, right?
Yeah, you can generate a lot more power from a smaller amount of fuel.
So it's a really powerful and efficient energy source. Let's say fusion power was readily available today, but we could just plug our homes into a fusion power plant.
Wow, that would be amazing.
It would. What do you think would be the most transformative applications? Where would we see the biggest impact?
Well, the most immediate impact would probably be in electricity generation. As we've been discussing, fusion power plants could replace those fossil fuel power plants, providing clean, safe, and basically limitless electricity.
That would be a game changer for our climate.
Absolutely. Cleaner air, a stable climate, energy security, the benefits are huge.
It's hard to even grasp the full scope of the impact.
It really is. But beyond electricity generation, fusion could transform other industries too, like desalination.
Desalination? You mean turning salt water into fresh water?
Exactly. Fusion could power large-scale desalination plants, providing clean drinking water to regions facing water scarcity.
Wow, that would solve a lot of global problems.
It could also revolutionize industries like transportation and manufacturing, leading to more efficient and sustainable processes.
So we're talking about a cleaner, more sustainable future across the board.
Precisely. And let's not forget about space exploration.
Oh yeah, fusion-powered rockets.
Fusion could enable us to travel to distant planets and stars in ways we can only dream of right now.
It's incredible to think about all the possibilities.
It really is mind-blowing. But it's important to remember that fusion still has a long way to go.
Right, we need to stay grounded.
There are challenges and even risks along the way.
What kind of risks?
Well, one concern is the management of radioactive materials, particularly tritium.
Tritium.
It's a key ingredient in the most common fusion reactions.
So even though fusion produces less radioactive waste than fission, there are still safety and environmental concerns to consider.
Absolutely. We need to be aware of those risks and develop responsible and safe ways to handle them.
It's a reminder that no technology is completely risk-free.
That's right. But the potential rewards of fusion, they're so significant that it's crucial we continue investing in research and development to mitigate those risks and ensure responsible implementation.
It's all about finding that balance, weighing the potential benefits against the challenges and uncertainties.
Right. It's a journey of discovery and innovation.
But it's a journey worth taking. I mean, the possibility of clean, abundant energy for generations to come, that's a future worth fighting for.
I couldn't agree more. And with the remarkable progress we're seeing, I'm optimistic that fusion will eventually fulfill its promise.
Well, this has been an absolutely fascinating conversation. Thank you so much for sharing your expertise and insights with us.
It's been my pleasure. I'm always happy to talk about fusion.
Thank you for joining us on this incredible journey. We'll see you next time for another exploration of a topic that's sure to ignite your curiosity and expand your horizons.